Howdy everyone, welcome to Computer Graphics, Animation, and Simulation. In this video we're going to take a look at how simulations work. Let's start with an overview. We're going to cover four main topics today. First, we're going to talk about what a simulation loop looks like. Then we're going to talk about how to use state vectors. Then we're going to talk about some basic integration. And finally, we're going to use a Newtonian Physics example of a dropping object in one dimension. Let's take a look at what a simulation loop is like. So first of all, when we're talking about simulation, we're essentially talking about two components, a model and a simulation. So a model is a set of laws or rules governing how something is going to behave or operate, while the simulation is essentially how we encapsulate that behavior in a framework that allows us to predict the evolution of the behavior. So there's essentially 5 steps to this. First, we want to initialize the simulation, so we'll set up all the objects, all the variables. Then we want to start the loop by introducing a time step. This can be a constant, or we can just go based on frame rate. Next, we want to maybe check for boundary conditions. For example, we might want to check for collisions, make sure that things aren't outside of the acceptable range of values. Then we will update state vectors, and we'll discuss state vectors next. And finally, we'll just keep repeating this process over and over again until the simulation is finished. Sometimes this is just a matter of quitting the program, or maybe we hit a stop button, or maybe we have a certain time limit that we need to evaluate. So let's talk about state vectors. So one of the problems in a simulation is that we'd like to express the state of the entire system, but we don't want to do it in a haphazard way. So we essentially want to use a state vector, which is a type of vector who we use all the elements to record all the important information. So let's say we have a set of objects, and we want to use a state vector to contain what each object is currently doing. So we might include things like position or velocity, mass, etc. This basically enables us to maintain a consistent or a coherent notion of what the entire system is doing at any given time. With this concept in mind, let's go on and talk about integration. So integration, we'd like to use the example initially of basic Euler integration, where we simply just add the quantity of change at every step. So let's just say we're trying to simulate a car, for example. We might use the elapsed time between frames to control the speed of the simulation. And so we would just use a basic integration step where we would say that the next value of x is given by the current value of x plus whatever the current value of velocity is times the time step. Then we'll update the velocity, and we'll say that the next value of velocity is equal to the current value of velocity plus the current acceleration times the time step. And we'll just continue doing these operations. So we might set the acceleration based on current forces after this, but there are numerical problems that may occur, and we have to consider other things. For example, what if the time step varies? Or what happens if we choose to update the next version of velocity before we update the position? What could possibly happen? So let's think about this more. There's some questions I think that you should have in mind when you're thinking about how integration is working. For example, do we update velocity before or after the position? What about updating the acceleration before or after velocity? How big should the time step be? Should we control how small it is or how large it is? Or do we control a maximum size that it's allowed to be? Or do we keep it fixed? There's lots of considerations to keep in mind. So let's see how this works from a Newtonian physics standpoint. So we know that force equals ma. That's one of the laws, one of Newton's 3 laws of motion. And we might have the force of gravity. So we would put this in an equation that says our force is our total force equals the force of gravity. So then we can just simply get rid of mass because it's irrelevant in this particular case. And so our acceleration is just simply equal to g, or minus 9.8 meters per second squared. So we can take a look at the steps to come up with the equation for motion here. And we have that starting with acceleration, we integrate acceleration with respect to time, and we would get that velocity equals some initial velocity plus acceleration times time. And then we can get the position by integrating this equation, and we find that whatever our current position is, it's the starting position for our object plus the initial velocity times time plus the 1/2 at squared. So this is how our acceleration changes over time. So let's say we have an object, maybe a cylinder, and we want to model it falling. So we would say the initial conditions are that x naught equals 0 meters, and the initial velocity is 0 meters per second, and the acceleration is minus 9.8 meters per second squared. So if we were to use this in our simulation standpoint, we would say, let's go ahead and update the velocity and just use the equation for velocity to do that. And then we can calculate the next position of x. So let's find out what will happen if we do this particular type of integration, if there are any kind of numerical errors. So let's look at some numerical issues that are going to creep up. First of all, let's start off by looking at an example of using a time step of 0.1 seconds per step. At 1 second, we're going to find that the position of our cylinder is at minus 5.39 meters. But if we actually use the integrated equation we calculated from the previous slide, we have that the actual position should be minus 4.9 meters. So maybe our problem is we're just using too big of a time step. So let's half it. Let's use 0.05 seconds as our time step. We'll find that our x has gotten closer. We're at now minus 5.145 meters, but that's still not good enough. And this is a issue with simulations because we might look at it and it might look realistic. However, the values over time obviously are not going to be accurate. So let's take a look at using 60 frames per second, so 0.016666 seconds. We will have that x equals minus 4.982 meters. This is a lot closer, but it's still a little bit off, and that kind of alarms me. But let's see what happens if we increase the speed of the simulation to faster than a frame rate, or 0.01 seconds. We'll have that x equals minus 4.949 meters. So we're getting close, but this is going to create a lot of extra computation if we're just trying to get an accurate number. And in fact, we can find that maybe the problem has to do the order of updating the velocity. So let's say that we're going to update x now using the old version of velocity instead of the new version of velocity. We should expect this number to be smaller, and in fact we find it to be minus 4.851 meters. So it's kind of bouncing above and below depending on whether we use the next version of velocity or the previous or the next version of velocity. So let's take a look at an alternative way of doing this Eulerian integration step. So let's look at a different integration technique. What we're going to do, since we noticed that the previous and next values of velocity were above and below where we ought to be, how about we try taking the average? In other words, let's think about this problem in terms of maybe it's just that we don't know what the next velocity is supposed to be, and that's what's causing the problem. And so we're going to find out that if we use a time step of, say, 0.1 seconds, we're going to find out that our x actually equals minus 4.9 meters, which is exactly what our answer is supposed to be. And if we had used the finer grained step of, say, 0.01, then our x will also be minus 4.9 meters. And so all this is to say that the method that you approximate your solution can have profound effects on the accuracy of our solution. So maybe it's good enough for some issues, but that doesn't mean that it's going to be the best solution. Now, this particular integration technique works because our acceleration is fixed. But later on in this course, we will probably take a look at a different integration technique which can handle things like changing acceleration as well. And so, with that in mind, I'd like to go ahead and thank you for watching this video, and adios.